Hello and welcome back to this channel. This is Professor Rajesh Varapte, a book author of 25 plus engineering books. Dear students, in the earlier video, we have studied the node analysis, that is KCL, Kirchhoff's current law. If you haven't yet watched that video, I will provide the link in the description box. Do watch that video. Today's topic is concept of supernode. There is a common mistake. Without observing the supernode, students are directly applying KCL, which is very wrong procedure. Entire problem can be wrong. Now, first thing is, in this video I will teach you what is a supernode, how to identify it, and in case of supernode, if you can't apply KCL, then what are the techniques how to solve this. What is a supernode? If the definition is, if a voltage source is directly connected to the node, then it is called as supernode. In case of supernode, do not apply KCL at supernode. Keep in mind. We'll solve some numericals, then this concept will be clear to you. If you can't apply KCL, then how to solve it? Generate equation of node voltage in terms of connected voltage source, and then for another nodes, you can apply node analysis or KCL. Let us solve few examples so that this concept will be clear to you. Consider a problem. Let us say this is the given network and it is asked to calculate voltage V0. V0 is the output voltage. In the question, nothing will be mentioned whether it is supernode or not. We have to identify it. First step, recall the steps what we learned in node analysis. As usual, this bottom line is considered to be grounded, connected to the ground. Now, in the given circuit, we have to identify how many nodes are there. So let us first identify the nodes. This is one node. Node is a junction where different branches are connected. So this is one node. I will mark this node as VA. Any node notations will do. This is one more node. Let us say this notation is VB. This is one more node. Let us say node voltage is VC. All these things, VA, VB, VC, are called as node voltages. These are the three nodes, and it is asked to calculate V0. V0 is the output voltage. Indirectly, V0 is the voltage across 2 kilo ohm. This is one step. We have identified the nodes. Next, in the entire diagram, in all branches, we have to mark the branch currents. See, this given current source is having value 2 milliamperes. I will keep it as it is. I don't need any notation for this because this is already a current. So through this branch, 2 milliampere current flows. Now, consider this branch. Let us say this current is I1. Say this current is I2. How I am choosing the arrow? See, I don't know in between V and VB which is larger. So randomly I am considering the direction of I1 from left to right. Any direction will do. I2 is towards downward because usual notation is that current flows towards ground. Then say this current is I3. This current is I4. What about this branch? There is no resistance, so I am not marking any current for this branch. Now the most important thing, there are three nodes. We have written the notations VA, VB and VC. So next step is I need to apply the KCL. Before that, in the diagram itself, we need to write the values. Recall the basic things. How to write the values? If this is the resistance having value R, at one end voltage is V1, at another end voltage is V2, and I am considering that current flows from V1 to V2. Then according to Ohm's law, we have the basic equation I is equals to V upon R. In this case, since the current I have marked is flowing from V1 to V2, I will say this current is V1 minus V2 upon R. Very simple. Depending on the direction of current, I have written V1 minus V2 upon R. Larger voltage minus smaller voltage divided by resistance. So look at current I1. So for current I1, if I want to write equation, at one end of I1 is flowing through this 1 kilo ohm resistance. At one end of I1, I have voltage VA. At another end, voltage is VB. So it will be VA minus VB divided by value of resistance, which is 1 kilo ohm. That means it is 1000 ohm. So I am writing 1000. So this is the value of I1. I will write these values in the diagram itself. So this value is VA minus VB upon 1000. This is the value of current I1. Similarly, for current I2, I need to write all the values of current in terms of voltage. So for current I2, at one end we have voltage VB, second end is grounded. So this current I2, I will write it over here, is VB minus 0. Simply you can write VB divided by 1 kilo ohm, that is 1000. This is the equation for I2. For I3, same logic. At one end I have VB, at another end I have VC. So this can be written as VB minus VC upon 1000. This is the equation for I3. Now for I4, at one end node voltage is VC, another end, this is same line which is grounded. So for I4, I will write it over here. It can be written as VC minus 0 upon 2000, because value of resistance is 2000. So up till now what we did, we have assumed some currents, then we have marked node voltages VA, VB, VC, and we in the diagram itself we have written the expressions of current in terms of voltage. Now next part is I have to solve this numerical using KCL, that is Kirchhoff's current law. It is called as node analysis as well. Look at first node, at node VA. Now do remember this basic thing, a common mistake done by almost every student. If there is a only voltage source, there is no resistance between this node and voltage source, it is called as a super node, where node analysis cannot be applied. That means node VA is super node. So I will write it like this: VA is super node where I cannot apply KCL. Then by explaining this concept, I already told you, if it is a super node, don't apply KCL, but generate one equation. Now make the thing simple. This is the point where I have marked VA. Now this is the voltage source of value 12 volt. Positive of voltage source is directly connected to VA without any resistance. That means it is the same thing. So since positive of this voltage source is connected to VA, I will simply write the equation as VA is equals to 12. This is equation number 1. Very simple trick, how to memorize it. If voltage source is directly connected to any node, in between there is no resistance, it is called a super node. Then directly write that node voltage is equals to available value of voltage source. So I have written VA is equals to 12. And then onwards, do not think of this node, because we have generated one equation. For other nodes, we can well apply the KCL. Now I will write it like this: at VB, I need to apply KCL at VB. Recall the basics of KCL. What is the basic equation? Incoming currents is equals to outgoing currents. This is the basic equation of KCL or node analysis. Incoming currents is equals to outgoing currents. At node VB, incoming current means current flowing towards VB. Incoming are I1. This is the only one current, so I will write I1 is equals to, at VB, what are outgoing current? Outgoing current means current going away from VB. It is I2 and I3. So I will write it I2 plus I3. This is the equation I have written by applying KCL, that is node analysis. Now in the diagram itself we have put the values. So I1 is VA minus VB upon 1000. Simply put the values. VA minus VB upon 1000 is equals to, value of I2 is VB minus 0. So simply I will write, this is VB minus 0. Simply I will write VB upon 1000 plus equation of I3. I3 is VB minus VC upon 1000. Now we have to simplify this equation. At both sides we have 1000. So this 1000 can be easily cancelled. So next step can be written as VA minus VB is equals to VB plus VB minus VC, because this 1000 is cancelled everywhere. Now transform all these terms at the LHS. So it can be written as VA minus VB minus this VB plus VB becomes 2VB. So I will write minus 2VB. Then this is minus VC. If I will transfer it at the LHS, it becomes plus VC is equals to 0. So it can be written as VA minus 3VB plus VC is equals to 0. One more common mistake that you need to avoid. After writing this equation, we can easily understand that there are three unknowns. So, to reduce number of unknowns, use the simple trick. From equation 1, we have VA is equals to 12. So, instead of using notation, wherever VA is there, I will simply put this value. So, next equation will be 12 minus 3VB plus VC is equals to 0. As usual, be habited of transferring all the constants at the RHS. So, equation can be written as 3VB plus VC is equals to minus 12. Say this is equation number 2. I have applied KCL at node VB and I have got this equation number 2. Next part is we have to apply similar procedure at node VC. Do remember in the question it is asked to calculate V0. V0 is same as VC because there is no resistance in between. So if you calculate VC you will get indirectly answer of V0. Alright. So I will apply KCL at node VC. Same logic. Incoming currents is equals to outgoing currents. Look at this node. What are incoming currents? This 2 milliampere is one current. I3 is another current. So I will write it as 2 milliampere, that is 2 into 10 raised to minus 3 amperes, this current, plus I3 is equals to outgoing currents from this node VC is I4, so I will write it as I4. Similar to the earlier case, just put the values of I3 and I4, so it is 2 into 10 raised to minus 3 plus value of I3, this is VB minus VC upon 1000 is equals to value of I4 is VC minus 0. Simply I am writing VC upon 2000. Now to make the thing simple, at this stage itself, I will simplify it, multiply both sides by 1000. Multiply by 1000. Just for simplification purpose. So this 10 raised to minus 3 and 1000 gets cancelled. So I will get 2 plus VB minus VC because I am multiplying it by 1000 is equals to VC upon 2 because I am multiplying it by 1000. So if you simplify it, you will get this equation as VB minus VC by 2. I have transferred this VC by 2 at the LHS and we need to transfer constant term at the RHS is equals to minus 2. So this equation can be written as VB minus 1.5 VC is equals to minus 2. Say equation number 3. Now you just have to solve equations 2 and 3 on the calculator. So you will get directly answer of VC, that is VC is equals to 5.1428. It is the voltage, so its unit is volt. And just now I told you VC is same as V0, so you can well write this notation as V0. So this is the final answer of V0. Let us solve one more numerical to get this concept more clear to you. The next numerical is find current through 3 ohm using node analysis. This is the given network. Without thinking whether it is supernode or not, let us follow our normal procedure. So there are 3 nodes. This is first node. I will mark node voltage as VA. Second node VB. Third node VC. Any notations will do. Now we need to assign the currents in each branch. This is already a current source, so I am not making any other notation. So this current is 1 ampere. Through this branch, let us say current is I1. Through this branch, say I2. This is I3. This is I4. Like the previous sum, directions can be random, but as far as possible, think like this: current flows towards ground, so I3 is towards ground. This bottom line is by default connected to ground. Alright, next, how to think? Keep in mind, as I said earlier, if there is any node where voltage source is directly connected, it is supernode. This is a current source where current source is directly connected to VA. It is not a supernode. It should be a voltage source. Look at VC. Here voltage source is directly connected. There is no resistance in between. So VC is called as supernode. What we learn, since VC is supernode, initially while starting the numerical itself. So mark this as supernode and write Vc is equals to 5 volt like the earlier case. Very simple. Plus terminal of this 5 volt is directly connected at Vc, so I have written Vc is equals to 5 volt. So whenever there is a supernode, directly assign the value of voltage source to the node voltage, so Vc is equals to 5. Now for remaining nodes I need to apply KCL, but before that in the diagram itself I will write the values. For this I2, at one end voltage is Va, at another end it is Vc. So for I2 I will write the equation as Va minus Vc upon 5. This is the equation for I2. Then for I1, at one end node voltage is Va, at another end it is Vb. So for I1 it is Va minus Vb upon 2. This is equation for Ia. For I3, I will write it over here. For I3, equation will be Vb minus 0. So simply Vb upon 3. Then for I4, it is Vb minus Vc upon 1. So for I4, it is Vb minus Vc upon 1. That means simply we can write Vb minus Vc. So what I did, after marking the notations in terms of current and voltages in terms of for node voltages, I have written all the things in the diagram. Let us apply the node analysis. So first calculation at Va, same rule, incoming currents is equals to outgoing current. So at Va, incoming current is 1 ampere, outgoing currents are I1 and I2. So I will write it like this: 1, that is incoming current, is equals to outgoing currents I1 plus I2. Like the previous case, simply put the values of I1 and I2 which we have written in the diagram. So this is 1 equals to Va minus Vb upon 2. Value of I1 I have put. Then value of I2. Value of I2 is written like this: plus Va minus Vc upon 5. Now you need to simplify this equation. While simplifying it, keep in mind there are 3 unknowns Va, Vb, Vc. To reduce down the calculation, we can put the value of Vc, which is 5, over here. So equation can be written as 1 is equals to 1 half Va. This is Va minus Vb upon 2. I have written it as 1 half Va minus 1 half Vb plus 1 by 5 Va minus value of Vc is 5 upon 5. So this becomes 1 is equals to 0.5 Va minus 0.5 Vb plus 0.2 Va minus 1. Let us rearrange all the terms at unknowns at LHS and constant terms at RHS. So equation can be simply written as 0.7 Va, I have added these two terms, minus 0.5 Vb, this term, is equals to, if I will transfer this minus 1 at the LHS, it becomes plus 2. I have just interchanged the term, so it is plus 2. Say it is equation number 1. This I got after applying KCL at node Vb. Same technique, now I want to apply KCL at node Vc. So at Vc, same rule, incoming currents is equals to outgoing currents. But what we learned, you don't have to apply KCL at Vc, so I need to apply it at Vb, because for Vc we have directly written the answer. So for Vb, incoming currents are I1, outgoing currents are I3 and I4. So I will write the equation as I1 is equals to I3 plus I4. Incoming current is I1, I am talking about Vb, outgoing currents are I3 and I4. Simply put the values. So I1 is this value, Va minus Vb upon 2 is equals to I3 Vb upon 3. To make the thing simple, I have written all the values in the diagram itself, plus I4. What is the value of I4? I4 is Vb minus Vc upon 1. Let us simplify this equation. So it can be written as 1 half Va minus 1 half Vb is equals to Vb upon 3 plus Vb minus Vc. So it becomes 0.5 Va minus 0.5 Vb is equals to 1 by 3 is 0.33 Vb plus VB minus VC. The value of VC, we need to put it, that is equals to minus 5. If you rearrange the terms, I mean if you transfer all the constants at the LHS, so it becomes 0.5 VA, then this is 0.33 and 1.33, and if you transfer it at the LHS, there is already minus 0.5, so it is 1.83 VB is equals to minus 5. This is equation number 2. Now remaining part is pretty simple. Once you will get equations 1 and 2, there are 2 equations and 2 unknowns. You will have to solve it on the calculator. So the answers will be, what we are interested in. It is asked to calculate current passing through I3. So we are interested in answer of VB only. So if you do the calculation on calculator, answer of VB will be 4.36 volt. This is the answer of VB. Now it is asked to calculate I3. So in the diagram itself we have written the value of I3. It is VP upon 3. 4.36 upon 3. So answer of I3 will be 1.45 amperes. This is the current I3 which is flowing downward. If you want, you can write the direction like this, making a downward arrow. So this is the final answer. Dear students, these are the 2 types of variations as far as this supernode concept is concerned. So if you have liked this video, please don't forget to smash the like button. Thank you very much.